Welcome. I will present to you today my talk about rooted quantum circuits. This is all from a paper that we did at the University of Oxford with Hlér, Kristjánsson and John Barrett, and that you can find on the arXiv. It will be published soon. This story starts with quantum circuits, which you probably all know about. Now, we found out that actually some scenarios cannot be described adequately with quantum circuits. And I'm not talking about indefinite causal order, I'm talking about something else. Therefore, what we do here is to propose an extension to quantum circuits that has the form of rooted quantum circuits, and that can describe all these scenarios. You have an example of a rooted quantum circuit right there. It could be applied to the study of coherent control, to the study of causal decompositions, and also, even though it's not indefinite causal order, it could be applied to the description of indefinite causal order. Now, you're all asking the same question, I suppose. What's the issue? Why cannot I always use standard quantum circuits? We are going to provide here two examples of scenarios and lines of research in general that standard quantum circuits cannot adequately describe. The first of these lines of research is that of superpositions of trajectories. It's quite simple, really. It's a scenario in which you have a particle and a control qubit, and the control qubit will coherently control where the particle goes. So the particle can go either through Alice's path or through Bob's path, each path having a channel that you can say is under the control of either Alice and Bob. So here, V1 and V2. Now, you have to say, to describe this scenario, that whenever, for example, the particle goes through Alice's path, then Bob has to get something, so Bob gets a so-called vacuum state, orthogonal to the possible states of the particle. And it is very important for this scenario that there's always only ever one particle traveling, so Alice and Bob's actions cannot modify the number of particles. Now, it is important to acknowledge that this is not an outlandish scenario. This is a very natural situation that you could, for example, find on any quantum optics tabletop experiment, right? Photons going in superpositions of trajectories. Now, this scenario has quite interesting features, and in particular, two features that we are going to describe. Let me also say that it has been studied in the past. Here's a very non-exhaustive list of references. It's interesting to note that in the second of these references, it was already pointed out that standard quantum circuits cannot really describe this scenario adequately. And if you are interested in its application to coherent control, you can also watch my other talk at UPL. All right, so the two major features of this scenario are so-called sectoral constraints and sectoral correlations. Now, what are they about? The first one, sectoral constraints, is just about what I talked to you about, the fact that Alice and Bob in this scenario cannot modify the number of particles. Therefore, if you take, for example, Alice's wire, its Hilbert space is partitioned between a one-dimensional vacuum sector corresponding to the vacuum state and a d-dimensional one-particle sector. And Alice's actions, V1, her operation, has to preserve the sectors. It has, in some sense, to be block diagonal. And you could also describe this in the theory of general CPTP maps if you want to have noisy channels. That's the first thing. The second thing is sectoral correlations. And sectoral correlations you can find if you look at a given slice of this scenario, by which I mean, for example, taking Alice and Bob's wires together. Now, this slice is not a tensor product of Alice and Bob's Hilbert spaces. Why? Because there's only ever one particle. Therefore, this slice can only correspond to a direct sum of the particle being on Alice's side and Bob getting the vacuum, or the opposite. And that is not the whole of Alice, the whole tensor product of Alice's Hilbert space and Bob's Hilbert space. It is a strict subspace of it. Now, both sectoral constraints and sectoral correlations cannot be described neatly by standard quantum circuits. And that's, let's say, an intuitive way of seeing why standard quantum circuits cannot describe this scenario adequately. There are some neater ways of arguing for it that are described in the paper that I don't have time to describe here. But of course, you're very welcome to ask questions about this. So therefore, this diagram that I was showing you on the left is actually not a proper diagram. You cannot, this is not a proper representation of this scenario because standard quantum circuits cannot do it. All right, now let's go to our second example. Our second example comes from a very different line of research, which is very interesting in itself. And this line of research is that of causal decompositions of unitaries. This line of research concerns itself with the relationship between, on the one hand, the causal structure of a unitary channel, that is the fact that some of its inputs cannot influence some of its outputs, and on the other hand, its compositional structure. So here, for example, if in U, A cannot influence D, saying that is equivalent to saying that U can be decomposed in this form. This is a known theorem. So there is an equivalence between the causal structure of U and its compositional structure. Now, the line of research of the causal decompositions of unitaries asks itself the question of, is there an equivalence in general? Now, this is still a conjecture, but it has been proven in numerous cases. But what is really interesting is that in some of these cases, the compositional structure had to be expressed not in standard circuits, but in so-called index matching circuits. And a good example of that is the diamond diagram that is described in the reference that you can see at the bottom. And so in this diagram, for this causal structure in which essentially you have a left wire and a right wire that cannot interact in a unitary, but they can both interact with the middle wire, this causal structure is equivalent with the compositional structure that you can see on the right. But this compositional structure that you see on the right cannot be written in terms of standard quantum circuits. The equivalence would not hold if you wrote it in terms of standard quantum circuits. It has to be written in so-called index matching circuits. Now, I won't have time to describe index matching circuits in detail here, but the point is they have exactly the same features as the ones we saw in the first scenario. That is, they fundamentally rely on the existence of sectorial constraints and sectoral correlations. But index matching circuits in the past works had only been described in examples. There was no systematic description of them, a systematic framework to encompass them. And therefore, this is also what we provide in our paper. All right, so now maybe you're convinced that there's an issue. Now the question is, how do we solve it? Well, you're at the right place because precisely this paper is about providing a solution, the rooted quantum circuits. Okay, how does it work? The point is to have some stuff that will encode the sectoral constraints on linear maps. So the fact that some sectors, some subspaces of the input and output Hilbert spaces cannot be connected by the linear map. Now, to describe this kind of structure, we can use an object that is called a relation that probably a lot of you will already know. That is used to model connections between the elements of two sets. So the idea here is that, for example, if you take ZA to be the set of labels of all the possible sectors of an input Hilbert space, and ZB to be the labels of the sectors of the output Hilbert space, you can describe sectoral constraints by just drawing arrows between ZA and ZB and saying that whenever there's no arrow, then the underlying linear map is not allowed to connect these sectors. And so this bunch of arrows that you draw can be described as a relation, which is an object that can be composed in sequence and in parallel. I mean, in general, it has all the structure of a diagrammatic monoidal category, for those of you who know about category theory. And something that is interesting too for us is that it can be written in terms of Boolean matrices. So a matrix whose indices are the elements of the input and output sets. And that takes value in the semi-ring of Boolean. So value 1 corresponds to the fact that there is an arrow, a value 0 corresponds to the fact that there is no arrow. Another point is that we are going to use relations to describe roots. So roots are just the relations that are endowed with the interpretation of encoding sectoral constraints for linear maps. And now that we have this, we can describe our main element of our framework, rooted maps, which just correspond to pairs. Pairs of first a root, and second, a linear map, which by definition has to follow the root. And by following the root, we just mean that the linear map has to satisfy the sectoral constraints that this root encodes. And rooted maps have to be maps between not exactly Hilbert spaces, but partitioned Hilbert spaces. That is, Hilbert spaces with a preferred partition that we will write in this way with superscripts to denote the partition. Now, you can define a structure on rooted maps by just defining all operations, that is compositions and products, the dagger, etc. All these operations you define pairwise. And once you do that, you get a dagger symmetric monoidal category. That is, for those of you who don't know about it, the main point of it is you can describe this in terms of circuit diagrams, which is really nice because what we wanted from the beginning is to provide another framework that is in the same way as quantum circuits that can be described in a nice graphical way. By the way, for those of you who know about it, this also forms a dagger compact category, so it also admits string diagrams. All right, so what do these rooted quantum circuits look like? Well, that's the example I showed you at the beginning. That's an application of rooted quantum circuits to the description of the superposition of trajectories that I was describing as an example. Now, how does it work? First, the wires names have superscripts that denote, as I was saying, the fact that these Hilbert spaces are partitioned. And the linear maps now come with roots, and the roots are written as floating Boolean matrices that are floating next to the linear maps. So that enforces the description of the sectorial constraints in the scenario. So here, for example, the fact that Bob cannot modify the number of particles will be described by an identity relation as a root. That is a Kronecker delta. So Bob has to map the vacuum to the vacuum and the one particle sector to the one particle sector. So finally, you could ask, what about sectoral correlations? Well, we can actually also describe them using roots. And the point will be to enforce them by using roots that force you to only populate a subspace of a big tensor product. That's the main point of our paper, and that's the main description of it. Now, we do a lot of all other stuff in this paper. The first other thing we do, and this other stuff I will not have time to describe, so I will go quickly about it. The first thing we do is to define which maps are physical. That is the equivalent of isometries in standard quantum circuits. Now, these physical maps are described by what we call practical isometries. And there's some work to do about ensuring that the composition of two practical isometries is a practical isometry. That there's a condition on roots only that ensures it. The second thing we do is to enlarge, to also apply this to general channels. Because of course you could say, okay, now your theory is for pure quantum theory, but what if I have general quantum channels that are describable by CPTP maps? Now, the answer is you can do it. We do it in the paper, and it essentially works in the same way. So here, for example, you have quantum circuit for general quantum channels for the superposition of three trajectories, just to show you that this framework scales up nicely. And finally, you could ask, but what about these index matching circuits that I saw at the beginning for causal decompositions? Well, we proved that they form a sub-framework of standard quantum circuits, and therefore we give a nice systematic description of them, proving that, giving them a sound basis. That's all for me. I hope this, for example, can be interesting to some applications that you might have, and we'll be very happy to answer your questions on Slack. And I'll leave you with this very short summary of the paper and of the talk, and with the archive posting. Thank you very much.